In this video, we will be learning canonical forms. Canonical forms are special formats of state space representations. First, let's look at how a state space representation or state variable model is linked with a transfer function of the system or the model that represents the input-output relationship of a physical system. We know that given a transfer function, there exist infinitely many input-output equivalent state variable models. All of them describe the same system. We want to find the state variable model in a canonical form given a transfer function. This is our task. To do this directly, it is not that easy. Therefore, we need something to help us to do the job. And this bridge is built by a graphical model of the system. So the graphical model can be either a signal flow graph or a block diagram. I'll use the signal flow graph to explain how to link a given transfer function. Let's recall Mason's gain formula, which is the most important thing associated with any signal flow graph. In Mason's gain formula, you probably remember we have three quantities: pk, delta k, and delta. Delta is called the determinant of the graph. It is regardless of the loops or the forward paths. Whereas pk and delta k, they must be related to a particular path k, and k is the path index. In the development of a signal flow graph in the canonical form, we want to simplify the Mason's gain formula. To do this, we would like to make two assumptions. The first assumption we make is that all feedback loops are touching. This is our first assumption. The second assumption we want to make is that these feedback loops touch all the forward paths. When all the loops are touching each other, we won't have any two non-touching loops or three non-touching loops. Therefore, in the delta formula, only the sum of feedback loop gains, the terms in the first bracket, are remained. And all the other brackets do not exist anymore. Now let's look at how the second assumption simplifies Mason's gain formula. When all the loops touch all the forward paths, delta k becomes 1 for every forward path. Therefore, you don't really see the delta k term in the simplified version of Mason's gain formula, which is given by this one. And in the development of the signal flow graph in the canonical form, we only use the simplified version of Mason's gain formula. It is better to understand how this is done through an example. Let's consider a fourth order transfer function given by this. If we divide the highest order term of s by both numerator and denominator, we get this. Now let's compare what we just derived with the simplified version of Mason's gain formula. We can immediately see some similarity between them. Let's look at the denominator. The first term is unity in both expressions. Then we have the summation. And you may ask, in the simplified version of Mason's gain formula, it was a minus sign, whereas here it's all the plus sign. But this is easy to explain. If all the feedback loops are negative feedback loops, then we get all the plus signs. Numerator in the simplified version of Mason's gain formula basically says sum of forward path gains, and that is shown by the term here. And this term means we only have one forward path because it is a single term. Another thing I would like to draw your attention to is that for this fourth order system, we should only have 4 state variables, x1, x2, x3, and x4, because the order of the system matches the number of state variables. It is important to note that the building block of the signal flow graph in a canonical form is the integrator. The integrator here is expressed by 1 on s, or s to the power of -1. When we have the derivative as the input node, after integration, we get back the original variable. That is why 1 on s, or s to the power of -1, is an integrator. You may also notice we have these power terms of s to the power of -2, s to the power of -3, and s to the power of -4. When we have them, basically, they are a result of a cascade of integrators. So for s to the power of -2, basically we cascade 2 integrators. And we know that the integrator is illustrated by 1 on s. The best way to draw the signal flow graph is to divide it into the feedback loops and forward paths. The numerator of the transfer function gives us the forward paths. The denominator of the transfer function gives us the feedback loops. For this example, the numerator only has 1 term. Therefore, we only have 1 forward path, and this forward path is shown as a horizontal path from the input node US to the output node YS. The denominator has 5 terms. We ignore the first term unity. Instead, we concentrate on the other terms. And the number of other terms included in the numerator should coincide with the number of loops in the signal flow graph. And now we can say, apart from unity, we have 4 other terms. Therefore, we should have 4 loops. And when we draw the loops, we need to remember the 2 assumptions we made earlier. The first assumption is that all the feedback loops should be touching. Therefore, we draw the loops as nested loops to make sure that they touch each other. And that is shown by the signal flow graph on this slide. We also need to remember the second assumption we made earlier. That is, all the feedback loops should touch all the forward paths. And in this example, there's only 1 forward path. We need to make sure that all of these 4 loops touch the path. And that is also shown in the signal flow graph on the slide. So I hope you can also verify that this signal flow graph does correspond to the transfer function given on the top of the slide. On this slide, it shows you the block diagram of the same system. And we know that block diagrams and signal flow graphs, they convey the same information about the system. The only difference between them is the way the information is represented. After we draw the signal flow graph in the canonical form, we should specify state variables. How do we specify state variables? We specify state variables by looking at the rightmost integrator. And we always start from the rightmost integrator. We start writing the state variables from the output node of the rightmost integrator. Therefore, x1 should denote the output node of the rightmost integrator of this signal flow graph. Then we move to the second last integrator and we concentrate on the output node. And this output node should be denoted by x2. Then we move to the third last integrator and we denote x3 for the output node of this integrator. And same for x4. So the rule is we should always specify the state variable for the output node of an integrator. If the output node of an integrator is denoted by xi, then the input node of this integrator should be xi dot, the first order derivative of xi. After specifying the state variables of the signal flow graph, we are ready to write out the state variable model or state space representation. For this particular canonical form, there is a pattern. That is why we call this a canonical form. And the pattern is shown by the equations here. We say that x1 is this node, and it is output node of the rightmost integrator. And we know that the input node of this integrator should be x1 dot. So this node is also x1 dot. And we can say that x1 dot is exactly x2. If x2 is the output node of this integrator, then the input node of this integrator should be x2 dot. And you can see that x2 dot is exactly x3. And same for this one. x3 dot is exactly x4. And the input node of the last integrator from right is x4 dot. And x4 dot should be written in a different way because there's no x dot equals x5. How do we write the equation for x4 dot? We need to count the incoming branches to this node. And we can say from the signal flow graph, there are 5 incoming branches. And that is shown by this equation. All of these equations are the state equation SE. The output equation for this signal flow graph is easy. It is y of t equals b naught times x1t, which is given by the last node in the signal flow graph. If we want to write the matrix form of this state space representation, it should also be easy enough. We can see our matrix A is also very special. It is 4 by 4 because this is a fourth order system. It is special because the signal flow graph we have just drawn is a canonical form. It has a special pattern. So matrix A can be written as this. The first row of matrix A should come from the first equation of SE. The second row of matrix A comes from the second equation of SE. It is like this. The third row of matrix A comes from the third equation of SE. And the last row of matrix A comes from the fourth equation of SE. Again, when you write these elements in matrix A, you should have a good knowledge about matrix theory. Now, let's write B. Since this is a single input, single output system, matrix B becomes a vector. And this vector also follows a special format. It is 4 by 1. And matrix C for this SISO system becomes a row vector. It also follows a special format because it is a canonical form. Matrix D is 0. There is no direct link between the input and output. So these are the matrices to represent this state variable model. This slide shows you what I have just derived previously. Now let's generalize this to something more complex. What is shown on this slide is also a fourth order system. The denominator is exactly the same as the previous example. The difference exists in the numerator. In this example, the numerator has 4 terms. Therefore, we should have 4 forward paths. Now let's draw the signal flow graph in the canonical form for this fourth order transfer function. This is shown by the first graph on the slide. We need to remember the 2 assumptions we made earlier. All the feedback loops should be touching each other, and they should also touch all the forward paths. And when you draw the signal flow graph, you can see that these 2 assumptions are followed. Now I'm going to review to you the name of this canonical form. It is called phase variable canonical form. So when you draw the signal flow graph in the way I just demonstrated, you are getting the phase canonical form for the state space representation of the system. On the bottom of this slide, it shows you the block diagram of the same system. Now let's look at how to derive the state space representation of this phase variable canonical form. We start labeling the state variables from the rightmost integrator, and we only label the output node of the integrator. And that is shown by this. After that, we can write the state equation and the output equation, and they are shown by this. The matrix form should also be easy to obtain. Matrix A and matrix B are exactly the same as those in the previous example. Matrix C is different though, because in the numerator we have more terms. That is all about the phase variable canonical form of a state variable model.